Hello everyone. We are here to present our final review for our final year project. Our project title is Image Steg Analysis using Discrete Cosine Transform Residual. The group members are Aditya Venkatraman and KV Pranav, which is me. And our sincere thanks to our project guide, Dr. N. Subhashini. Now let us move to the introduction of our project. So let us see about image steganography and steg analysis first before diving deep into our main concept. So image steg analysis can be considered the science of analyzing images to distinguish images that contain hidden information from those that do not and attempt to reveal the hidden information. Existing as an analog to steganography, it is a complementary process that is essential to its existence. We know the importance that steganography holds in security domain predominantly and steg analysis in the means to both counter and improve the same. To truly understand the process of steganalisis, we must first dive into the steganography and entire secure communication process. Steganography is a technique of hiding secret or sensitive information within something that appears to be very normal to look at in a day-to-day life like usual image. A person will not be aware that there is any secret information present if they view that object that contains the hidden information. Steganography works by exploiting human perception because our senses aren't equipped to search for files that contain information. None of the steganography algorithm used today, meanwhile, achieve perfect security. This is due to the minor alterations that steganography methods introduced during the embedding process. These alterations may be used by an attacker to recognize altered image that is stego from the covers. Steganography involves using techniques and methods that allow for hiding of information within an innocent looking cover object which resembles the original cover object as much as possible. This enables the transmission of the generated stego object through an unsafe communication channel that could be intercepted by a third party. Steganography refers to the process of hiding information within a digital image. So yeah, before seeing this, there is two types of steg analysis. One is an active steg analysis and other is passive steg analysis. So to understand this concept, we need to imagine a particular situation. This is the situation of a covert communication process. Here, Anita and Smith are the two prisoners, while Elizabeth is the warden. Anita and Smith decide to communicate without speaking or writing, but they decide to communicate using steganography. Anita wants to send message to Smith, but Warden, that is the Elizabeth, just intercepts the image here in between. So the Elizabeth wants to check whether whether the image contains any sort of information. So she does a steganalisis process. If she wants to know what information is present in that image, she will do active steganalisis, and we can even remove that information from that image, and Smith won't even know whether that image had any information or not. In the case of passive steganalisis, Elizabeth will know whether the image has any information or not. That's it. That is 1 or 0, something like binary. This project mainly aims at passive steg analysis technique, and we are doing a targeted specific steg analysis because active steg analysis research isn't in advanced level, and there are research going on in very foundational level. So we are doing this in passive side. So the two steganography algorithm we took is JUnivard and UERD algorithm. Before that, we'll just see the motivation for our project. So the main motivation is due to the importance of digital image security in recent time, and the thing is the rise of steganography and evolving threats. That is, many kinds of viruses are being transferred, which are encoded in an image, and then the virus are being transferred, and other legal implications. These are some of the motivations which motivated us to do to work on this, to research on this domain of image steg analysis. So this is the steg analysis process. This is the cover image. This is the message, and this is the stego key. We combine them into one thing, which becomes a process of steganography, and we get the stego object. So stego object, by looking at the stego object, we will not know whether the information won't be visible to human naked eye. But if we use a stego key, we can just see what information is present there. And then if we perform Steganalysis on the Stego object, we can do binary classification, and we can easily identify whether the image is a Stego image or just a cover image. So our main, as I said before, our main objective of this project is to perform image tech analysis on images that have undergone JUnivard and UERD algorithm steganography using discrete cosine transform residuals of the image. So before going into our features and our proposed work, we'll just see what is JUnivard and UERD steganography algorithm, so that we can understand the concept much better. Over to Aditya Venkatraman, who will explain this pretty well.
So J-Union algorithm is a method for modeling steganographic distortion caused by data embedding. It mainly aims to provide a function that determines which region of the cover object are less predictable and harder to model. Changes introduced during steganographic data embedding in those areas are harder to detect than if they were introduced uniformly across the carrier. Through computation of relative changes of values based on directional filter bank decomposition, this method is able to detect smooth edges that are easy to model. Next step. Next slide.
Yeah, this is the process of JUnivard steganography. Aditya will explain.
So here are the steps involved in the J-Universe steganography algorithm process. The first step involves choosing a cover image. So select an image that will be used to hide the secret data. This image should be large enough to contain the secret data. The second step is to divide the cover image into blocks. Divide the cover image into non-overlapping blocks of size n into n, where n is an integer value. The third step is to select a block, that is to choose a block from the cover image for embedding the secret data. The fourth step involves dividing the selected block into subblocks, into non-overlapping subblocks of size m into m, where m is an integer value. The next step is to determine the threshold value, that is to calculate the threshold value based on the subblocks of the selected block. The next step involves to embed the secret data. Now we embed the secret data in the selected block by modifying the pixel values of the subblocks based on the threshold value. Now we have to repeat steps 3 to 6 until all the secret data is embedded in the cover image. The final step is to save the stego image. We save the modified cover image as the stego image, which now contains the hidden secret data. Yeah.
DCT residuals can be a very good feature to detect J-inverse steganography, where J-inverse steganography algorithm modifies the DCT coefficients of the cover image in a structured way to embed the secret image. Therefore, difference between the DCT coefficients of the cover image and the stego image can reveal the presence of hidden information, hidden messages. So next is the UERD algorithm. Over to Aditya.
So UERD is a steganographic embedding scheme that aims to minimize the probability of steganographically encoded information's presence being detected by minimizing the embedding's impact on the statistical parameters of the cover information. It achieves this by analyzing the parameters of DCT coefficients of given models as well as whole DCT blocks and their neighbors. Through this, the method can determine whether the region can be considered noisy and whether embedding will impact statistical features such as histograms of the file. Wet regions are those where statistical parameters are predictable and where embedding would cause noticeable changes. The scheme does not exclude values such as DC mode coefficients or zero DCT coefficients from being used when embedding, as their statistical profiles can make them suitable from the security perspective. UERD attempts to uniformly spread the relative changes of statistics resulting from embedding. UERD is a specific algorithm for hiding information within digital images. It is a lossless algorithm, meaning that the original image is not modified, and the hidden image can be retrieved without loss of quality. The UERD algorithm is based on the principle of uniform embedding, which aims to hide data in such a way that the distortion introduced to the cover image is uniform across the entire image. This helps to reduce the likelihood of the steganography being detected by the visual inspection of or steganalysis. Next slide.
So this is a proposed methodology. First step is the image dataset pre-processing, and then we apply DCT to that images, and then we get the DCT residuals by subtracting from the original image, and then we just flatten the data into a 2D NumPy array. We then design a neural network model for yeah, we design two separate neural network model. One is a 5-layer one, and the other one is a 3-layer one for based on for images which has two separate information densities. And the last step is the binary classification. So these are the three domains in an image. So we are going to see what why we decided to use the DCTR of the images as a feature. So we'll just see what are the three domains. The first one is a frequency domain where we just use the pixel values so by taking the Fourier transform. The other one is a texture domain where we use the Gabor filter residuals. And the third one is using the discrete cosine transform residual, which is the spatial domain of that image. So different research, various research has been going on, and we choose to use the DCTR based on our literature survey and other things and researches. So now we'll see what is DCT and DCT coefficients first. A DCT coefficient, DCT function is just expresses a finite of data points in terms of sum of cosine functions oscillating at different frequencies. And DCT coefficient is a quantized weight applied to each function's frequency. In Steganalysis, the DCT coefficients are analyzed to evaluate normal or expected frequencies within the file. So this is choosing this process is choosing our features for the image. This is Aditya will explain this while we are using DCTR. Yeah, we are extracting DCTR from the images. Aditya.
Image tag analysis using DCTR, which is also known as DCT residual, as features involves the use of discrete cosine transform, which we call as DCT, to analyze the changes made to an image through steganography. This process involves the following steps. The first step is to apply DCT to each block, resulting in a frequency representation of the block. The next step is to extract the DCT residual by subtracting the quantized DCT coefficients from the original coefficients. The third step is to collect the DCT residuals of all blocks in the image to form a feature vector for the image. The fourth step is to train a model using DCT residual feature vectors of both cover and stego images to distinguish between them. To classify a new image, extract its DCT residual feature vector using the same process as for the training data, and use the trained model to classify the image as cover or stego. Yeah, next slide.
So this is the dataset we use. So we use the dataset from Breakover Steganography system. This was available in Kaggle website, and we also got this as a reference in one of the research paper base paper we were using. So the photos, it had some around 10,000 black and grayscale images with no hidden data. The photos were then converted into JPEG with a quality factor of 75. Then there was one code which was available in GitHub, which used to generate the images with information density of 0.4 and 0.1 BPN SAC. We are using two steganography algorithm, that is JUnivard and UERT. And this we have given the source for that data set. And then we converted those into a CSV file. And then the data which was fed as the feature for the neural network model was in the form of a CSV file, that is a 2D array. So this is a neural network model design we use. First one is for the 0.4 BPN ZAC, that is 0.4 bits per per nanosecond AC, and the other one is 0.1 bits thing per NAC. It has around, yeah, this is a 5-layer model. First layer has 500 neurons, second has 250, and the third one has 150, fourth one with 100, and last one has 50 neurons. And we have added batch normalization layer, a dropout layer, and a few regularization in middle to avoid model getting overfitted. And this one, we just wanted to reduce the complexity of the model, to reduce the training time also. For this one was for 0.1 BPN SAC images. This one is 200 into 150 into 50. This has some batch normalization, and yeah, dropout layers in between. So this improved the model accuracy, efficacy. So this is the model description. The first model, yeah, I described this before. And the activation function we use is the ReLU function, and we use the Adam optimizer. First, we also used SGD, but Adam optimizer gave us some better results. And the learning rate is 1 into e power minus 4 seconds. A dropout rate of 0.2 was used, and in some places even 0.3 was used based on just to get better results and to avoid model overfitting and underfitting. So this is the evaluation results. Um, we got a model accuracy of 87.5 percentage for JNUAT steganography with a zero point 0.4 BPN ZAC density, yeah, payload, information payload. And we got a very high value. It was pretty impressive for UERD steganography with a zero point 0.4 BPN ZAC, around 95.4 percentage. But zero point 0.1 BPN ZAC, yeah, images with the zero point 0.1 BPN ZAC payload was very difficult to detect as it had only a little yeah, information. So the model couldn't work that well, even when the model was not that complex. But this is the best value we got. This has 53.8%, and for UERD zero point 0.1, we got around a percentage of say 73. And this is all the other metrics: precision, F1, recall, and other things. We have plotted all other results. Yeah, you can check here separately. This one is zero point 0.4 and this one is 0.1. Yeah, so for the discussion, so we discovered that the density of the inserted hidden data and chosen steganography technique had a significant impact on the performance. I said this before. We could achieve comparatively better results for images with low payload when the model was simple and not complex. When experimenting with several kinds of neural network, we also found batch normalization, adding a batch normalization layer could improve the model efficiency. The best optimizer was Adam, and I said all these before. Regularizer and dropout layers were added to prevent. And this is now the comes the end of our project. This is the application of image tech analysis. First one is for security concerns. Other one is yeah, mainly has many positives. Tech analysis allows us to monitor and identify a possible image that contains hidden information. So sometimes, as I said before, it could also recognize images that has a malicious content yeah, as information. So we can avoid that. It can also be employed by militants. As steganography can be employed by militants, so other threads to communicate within themselves. So steganalysis methods allows us to monitor the images which are shared by these local militant groups. And this is for authenticity check. This is a watermark images which signature can be identified. And this is a data recovery thing. So sometimes essential data like medical records embedded within medical images, etc., can be lost due to key misplacement. So in which technologies can allow us to try and crack the steganography to recover the information. This is the main difference between steganography and the cryptography. Steganography doesn't just change the information. Maximum the information may be converted into just binary, but in cryptography it is just encoded in some other form. It is just in encrypted, and the receiver should know how it is encrypted, and he needs to decrypt the information. But in steganography it's not that case. The receiver just has to have that steganography key, and he can just separate the stego and the cover object separately. This is the conclusion. We have now comes the end of our project. We have developed a neural network model, which has we have designed that to perform image tech analysis on images which had undergone JUnivert and UERD steganography. The model yielded a very good result in detecting information for images with 0.1, 0.4 bps of density. For the UERD algorithm, we got very good results. The image with less information payload were difficult to detect. This domain has very good scope for future works. JUnivert steganography algorithm offers a very good platform for research, as the detection of information in this algorithm is like we didn't get that impressive results using the steganalysis technique right now. But yeah, many steganography algorithms are in development. So more the number of steganography algorithms, more number of steganalysis research will be going on. So it has a very good scope for future. Thank you.